The following tutorials will teach you how to test a differential protection relay with the Advanced Differential Test modules. As an example, we will test a Siemens 7UT613 differential protection relay. In this tutorial, we will cover the test object and the global hardware configuration. You can test a differential protection device with the Differential Test module or the Advanced Differential Test modules. Since the Advanced Differential set offers more features, we will use these modules to test the differential protection device. For testing the Siemens differential relay, we will make use of a new OCC test document. The four Advanced Differential Test modules are Diff configuration, Diff operating characteristic, Diff trip time characteristic, and Diff harmonic restraint. We insert these four modules into the OCC document. According to Omicron's Ohm's law, we start with the test object. Fill out the entry fields in the Rio block device first. In our example, the protected object is a transformer. The CT ratio data is not relevant here since it has to be entered into the Rio block differential for all windings. The Rio block differential requires a lot of information, but once you have completed it, the testing of differential protecting becomes easier since all Advanced Differential Test modules make use of the same Rio block. The differential block contains 5 tabs. The first one is the protected object. The second one, the CT. In the third tab, you enter the information about the protection device. In the fourth tab, you draw the characteristic, and in the last tab, you enter the characteristic of the harmonic restraint. We start with the information about the protected object. In our example, the protected object is a 3-winding transformer. In the picture, you see its nominal values. Now enter the nominal values of the windings, including the vector group and the star point grounding. In our example, the vector group is YYND5, so the star point of the secondary winding is grounded. The nominal currents are calculated automatically from the power and the voltage values. In this tab, you enter the data of the current transformer. In the picture, you see the values of the CTs in our example. The star point of the CTs can be grounded towards the protected object or towards line. In our example, all star points are grounded towards the protected object. If at least one winding of the protected object is grounded, you can check the Use Ground Current Measurement Inputs box. Then the residual current will be generated on the configured output. Remember to enter the information about the ground CT nominal values. The Protection Device tab is where you enter the relay settings. Set the formula for the bias current calculation according to the relay manual. If you have no access to the manual, check the Test Universe help to see which bias current formulas are commonly used by the different relay manufacturers. We choose the formula for our Siemens relay with a factor of 1. The maximum test time restricts the time for each shot to protect your relay. The delay time is the time in between consecutive test points. It is used to give the relay time to reset. Next, we have to specify the current settings. Therefore, we have to look how the characteristic is built. Small differential currents are also possible under healthy conditions. They exist due to transformer magnetization, tap changer, leakage, and saturation effects. The addition of all these effects represents the maximum differential current that is possible under healthy conditions. The differential characteristic is an approximation to all these effects. In our example, the characteristic starts at the low set value, which is 0.25 times the nominal current. It rises to 6 times the nominal current, which is the high set value. Above this value, the relay always trips independent of the stabilizing current. Input these two values, low and high set, in the entry fields. Consider the operating time for the particular relay when it comes to specifying the time settings. Check the manual and enter the tolerances for the operating time and the differential current. The output values are calculated based on the reference winding and the reference current. Note that these settings have to match the relay setting. This ensures that the differential and bias current values calculated from the relay are equal to the values visible in Test Universe. If you selected Protected Object Nominal Currents, the currents calculated in the first tab will be used as reference currents. If you select Current Transformer Nominal Current, the CT nominal currents entered in the second tab will be used. Depending on the network configuration, zero-sequence elimination can be necessary in case of a single-phase fault. A typical case scenario is when a transformer is isolated in one side and grounded in the other. A fault outside the protected zone can lead to a false trip if no zero-sequence elimination is applied. This way, the zero-sequence components are subtracted so the currents at both sides are comparable. This operation may either be performed within the relay or by using interposing transformers. You have to specify if the zero-sequence elimination is applied so that Test Universe adds the zero-sequence component to the output currents if necessary. In other words, Test Universe reverses the relay's operation to ensure a perfect match between the calculated values from the relay and the test point specified in the test module. The Characteristic Definition tab is used to enter the characteristic. Each line segment is defined by its start and end points. Often these points are not given in the parameter set of the relay directly. Then you have to calculate them from the information available. The picture shows the points and slopes which are given in our example. From these values, we have to calculate the intersection of the lines by using the straight line equations. We get the 3 points required to define the characteristic in Test Universe. Check the Auto Init Start Point box to take the endpoint of the current segment as the start point of the next segment. The harmonic restraint characteristic can be defined in the Harmonic tab. You have to specify which harmonic component is subject to test. In this case, the harmonic restraint is activated for the second and fifth harmonic. The second harmonic is part of the inrush current that appears at the switch-on operation of a transformer. Enter the threshold for the harmonic restraint and define the tolerances. We keep the default value of 20% since it matches our relay settings. The fifth harmonic restraint prevents false tripping of the relay in the event of overexcitation. The threshold for this harmonic is set to 45% in our example. Click Update to validate any change in the entry fields. Our characteristics for the harmonic restraint are straight lines. If the characteristic is composed of several segments, you can enter the start and end points of each segment as we did in the Characteristic Definition tab. Now, confirm the dialog to save the information. The next step in Omicron's Ohm's law is the global hardware configuration. Since we are testing a differential protection, we need 6 current outputs, 3 for each winding under test. No voltage outputs are required. Name the outputs accordingly in the Analog Outputs tab. Regarding the binary inputs, only the trip command is required for this test.